Today we're on page 7 of the Chapter 12 AP Chemistry packet, and we're going to be talking about activation energy. Activation energy is the energy required to get a reaction going. So if I draw a quick picture here of a match, and you have a match right here and you want to light it, you know that it needs oxygen to light, and you're going to have O2 in the air colliding with the wood. But a match won't light unless you start it. You have to give it that initial activation energy. And that could be represented right here. So the match starts right here, and then you have to give it some activation energy to get it burning. And then once it burns, it actually releases more heat. And so that's why it is exothermic when it reacts. So this represents an exothermic reaction. And that's because it releases more energy than it had to absorb for the activation energy. In this case, the activation energy is from beginning to top right here. So that's going to be an activation energy of 60 kilojoules. And the delta H is from beginning to end. So the delta H is from beginning to end right here. And the delta H for this is going to be negative 20 kilojoules because you're going down in energy. You're losing energy or giving away energy from the beginning to the end. So it's a negative 20 kilojoules. Now you could add a catalyst into this. And if you add a catalyst, then for instance, this could go with an activation energy that's not quite as high. Let's say it goes up to only has to go up to 80. So it only has to go up to 80. Then you have a new activation energy, and that is only going to be 40 because you went from 40 up to 80. So that's going to be activation energy of 40 with a catalyst in the example. You'll notice, however, that the delta H will still be negative 20 because you have not changed the beginning or the end. The beginning is still 40. The end is still 20, so you're still at negative 20 for your delta H as well. All right, let's take this to talking about some reactions between two molecules. So let's suppose you had H2 plus F2 yields 2HF. If you look at the Lewis structure of these, you'll know that H is a diatomic molecule and F is a diatomic molecule. And HF is also really technically a diatomic molecule as well. And so, oh dear, I drew that wrong. This should be an H and an F. So I'm going to redraw this actually to match up something I want to show you. So let's do the H's, and I'm going to draw them vertically. And let's draw the F's vertically as well. So what has to happen here is that you're going to need to break the bonds between the H and the H. And you have to break the bond between the F and the F. And then you're going to form a bond between the H and the F. So in order for that to happen, these two molecules, the original hydrogen and the original fluorine, have to hit each other in the right orientation, where let's say the H and the F are right next to each other in both cases, and they have to hit with the right energy hard enough to react. So here, what I'm representing here right now is called an activated complex when it's the partial bonds. So let's redraw that over here and see what that would look like on a potential energy diagram. So you have your start, you have your activated complex here, and you have your ending. I'll draw it as an exothermic reaction. All right, so over here you have your H and your F separated from one another. Up here at the top you have your H and your F and your H and your F, and you have these partial bonds that are being broken, and then you have your partial bonds that are being formed, and this is what's called the activated complex. The activated complex is the complex where you have kind of everything all together in one big mess. It's not quite the reactants the way they were. It's not quite the products the way they're going to be. It's in between. So you have partial bonds going on. This activated complex is not stable. So of course that complex could break up into the products, or it could just break back up into the reactants as well. You have to have enough energy to get to make the activated complex, and then once you have that amount of energy, the complex could form the products, or the complex could go back and form the reactants again. And the only way to make this complex is to hit with the right energy and the right orientation. So this is a representation of the complex right here. Okay, next we're going to talk about this graph over here, and this is a slightly different graph. It's not the same as this graph on the right because you have different scales. On this graph on the right we had the potential energy and we had the progress of the reaction. Another name for that, by the way, is called the reaction coordinate. If you ever see that. Reaction coordinate. And this graph on the left is a different kind of graph. Name for this graph could be a Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. You could also liken this in an analogy to the track teams. Okay, so let's suppose that we are talking about high school track team right here at temperature 1. So this would, the area under the curve represents all of the runners. The more to the right you are, the faster the runner is. So on this blue curve, you could see that some runners are fairly fast, some are average, and some are fairly slow. Then you're going to have, let's say the college team would be the red curve. So you see that the average of the red is higher than the blue, meaning more to the right. So the college runner on the whole is average faster. So there are more faster runners on the college than the high school, and there are still some slower on the college team as well. Okay, so the average is what we care about right here, and the average is here for the temperature 1 and here for the temperature 2. So in chemistry, we're now talking about the speed of the molecules. The red temperature sample, this could be like hot water, and then the blue would be cold water. The average particle in the hot is moving faster than the average particle in the cold. Could you still have some cold particles faster than some of the hots? Sure. You could have a fast cold that's faster than a slow hot. That's possible. All right, now where does activation energy come in? Activation energy is the minimum amount of energy you need for the reaction to occur. The analogy for this would be like a meet of champions. So in the meet of champions, you have to make this cut to get into the meet of champions. So if you're on the college team, more kids are going to make it into that meet. If you're on the high school team, not as many kids are going to make the cut, but you'll still have some of each. Okay, so let's suppose the officials of the meet say, you know what, we don't have enough runners, we need to get more runners, we're going to lower the standard. So now you only have to be this good of a runner to get in. So now this would be the activation energy with a catalyst. A catalyst makes the reaction faster by lowering the activation energy. So on this graph, what's happening on the left is that the activation energy will move over or move left with a catalyst. But on this graph, a catalyst lowers the peak. So there are several graphs. You have to understand each type of graph. Okay? Next, we're going to move on to talk about how to find the activation energy for a reaction if you know the rate constants at different temperatures. So we're going to move into this example right here. So we could see this example here, and we're going to use our graphing calculator to do this. And I'm going to do this on another video so it's not too long.